Right, so in this video I will talk about binary search algorithm for array with no repeating elements which is sorted. So example of an array would be 1, 3, 5, 7, 10, and the indices are 0, 1, 2, 3, 4. The time complexity, as we will see, will be O log n for the solution, and space complexity will be a constant. So in order to solve this problem, first we will assign the two pointers left and right to the first element and to the last element, which is typically is done like this. R is equal, let's say this array is nums, so R will be len nums minus 1, and then basically what happens, we have a cycle where we take the middle element which is equal to L plus R divided by 2 is for operation. We take this middle element and we check first, we check it against the target. So target, in our case, let's say target is 7, and what happens is we take first we check if nums of m is equal to target, then we got our answer and we need to return our m. Okay, so what happens if our m element doesn't point to target yet? So I like to think about it in this way. So we have a certain, set of elements with L and R pointing to two sides of this set of elements. So elements are sorted. Currently our M is pointing to the middle. So first what we do, we mentally put our target here and check, is it true? So is the element which is in the middle of this set of elements, is our target is actually smaller than this guy? If it is, what we need to do, we need to put our R right here, so at the first element, which is less than the middle element. And the reason for this is that we already checked that our target is not equal to nums m in our first check, this guy right here. So we can write it as this: L if our target is less or equal than nums from m. What we do in this case, we need to move R right here, and we need to repeat the search operation. So we do it like this: R is equal to m minus 1. Okay, so what happens if it is not true as well? So what in this case, t obviously resides somewhere here, and that means that we need to move L right here to this element. So we can write it down as this: else L is equal to m plus 1. And that's it. So this algorithm is very simple, and it converges as soon as L becomes greater than R, or vice versa, R becomes lower than L. So this means that, let's say, example, so we have, let's say, L pointing here, R pointing here, and these are two consecutive elements. So M obviously will be pointing here as well, and if happens is if will be the second case, this guy. So if T will be somewhere here, that means we will have to move our R right here, and obviously this we had our L moved at this point for a reason, which means that our equation of L less than or equal than R doesn't hold anymore. And basically, the target doesn't exist in an array. So in this case, we just need to return -1. So another case, if T is somewhere here in the middle between L and R, and remember those are two consecutive elements. So in this case, by this algorithm, what will happen is we move L to here. So again, so this condition will not hold anymore, and we'll have to exit from our search cycle. So another case when it just happened that both L and R are pointing to the same element. This case, again, M will be here. We will first check if our target is equal to nums from this element. If it is true, we return as usual. If it is not true, again, we will have to move either right here or left here, and again, so our condition will not hold. Let's write it down somewhere here. While L is less or equal than R, execute this through checks, and if at the end we didn't find the element while this condition holds, we return -1. Okay, so as you can see, at each step of the algorithm we slice our array into half, which means that the time complexity is O log n, and as you can see, we don't use any stack here. There is a fixed number of pointers, so we can write the this is actually space complexity, and we can write space complexity as the constant. So there are a couple of common mistakes people do. One is it's not sort of a mistake, but rather than inefficient implementation of the algorithm, is when people use for some reason a recursive calls. So there are a number of reasons that could simplify the code, and that's why people use recursive calls. However, recursive calls will actually add on the space complexity, because every time we have recursive call, system will push current stack of variables into a current set of variables into a stack, and basically in the worst case we will repeat this push operation log n times, and the space complexity will be O log n. Even worse implementation is definitely a mistake is when people instead of passing the array and the boundaries left and right, they actually slice the initial array and pass it like the new copy of array in the recursive calls. So in this case, actually the overall time complexity grows to n or n, and the reason for that is that the very first call, what will happen is that it will push n divided by 2. It will first of all create and allocate the memory for the array, the half of the array, and will push the n divided by 2 elements to the next call, which is the or an operation, and in this case does make actually sense to use this interesting algorithm, because time complexity and space complexity will be still O n. Right, so this is all about it. In the next video I will talk about some different variants of binary search algorithm in the case when we have repeating elements, or when array is actually sorted but rotated.